Okay, good morning everyone. Today we shall continue with our exploitation of the energy momentum tensor. First, a few remarks. Well, you might have seen me make this mistake, refer to this expression, any such thing as this, especially this for this being the vector potential equal to 0, as a Lorentz gauge with a T here. That is a mistake, please. The name there should really be Lorentz without a T. If you find me make the same mistake in future lectures, just please take note. I fear I may still make the same mistake because a lot of times there's a lot of literature out there among people who use this same gauge, especially even in quantum field theory. The mistake is fraught everywhere, but I think it's a good thing that the correction be made so that one person can't be mistaken for someone else. That wouldn't be fair. So please, this is Lorentz gauge without the T there. One other remark I want to make very quickly is the fact that we have been using, okay, so for instance, look at this expression. If I have such an expression as this, of course, this is obviously a scalar. We have both contracted indices. If I want to differentiate this scalar with respect to, say, A sub rho sigma, I've used this trick that says the A rho sigma is the same thing as saying the A alpha comma beta, the A rho sigma, A beta comma alpha plus A alpha comma beta, the A beta comma alpha, the A rho sigma. I've explained this method over and over again. Even though I've tried to illustrate it, I just want to point to an exception to this rule. Normally, if you were to solve this, we wouldn't have a problem with this one. For instance, this is almost just of the same form or the same kind with that. And this will simply give us two chronicle deltas, alpha rho and beta sigma. Now, but in this case, it's not the same. And usually the traditional way will be to use some metric tensors to lower these two indices. And if we do that, then we can go ahead with solving them and then finally reevaluate the whole expression or term using those metric indices. But in recent times, especially in the previous lectures, I think about two lectures ago, I have shown that this expression in particular might as well be written as A alpha comma beta, the A but beta down comma alpha, the A rho comma sigma. So that in the end, this factor here is of the kind or the one we would really want to expect. Because in lowering these indices using metric tensors, we are just trying to get it in this form. And so, but instead of going through all that process of using metric tensors to lower them, you can simply just raise these ones and lower these ones in the form that, okay, for instance, if you have two contracted indices, one is always up and one is down. So the idea always is whatever metric tensor I use to raise this, or let me say whatever metric tensor I use to lower alpha, I can use to raise this alpha. And whatever metric tensor I use to lower beta, I can use to raise beta. We have shown this severally, and we will again use this style over and over again. And so this was just fine. So without using any extra metric tensors to lower this, I can just write this term as this and go ahead with the differentiation and everything looks just fine. However, there's a problem here which I think I should point out. We have shown this, especially I believe in our first lecture, that this, for instance, is equal to that, which is equal to minus that. So without being redundant, let me just work with this. Now you can see that I have mu nu on top and mu nu down, minus this same expression, but mu nu down here and mu nu on top. So if I were to use this method here, which has been convenient to me for a while, this method of trying to write this term as that, which has been very convenient and has been working fine here, you will want to ask, why then is it that we have this to be equal to minus that? It should be true then that when I just lower mu nu here, I can just raise mu nu on top, and I shouldn't have a minus sign. But you can see that this is just one exception. And one reason I can think of especially is the fact that the metric tensor, okay, first of all, we have the two indices on one object, not on two different objects. For instance, again, I would like you to just come with me on this object. The indices I have here, although I have it to be, this is A beta comma alpha. These two indices are not actually just on one sub-object. This might as well be written as the alpha A beta. So I have a differential operator and I have another one sharing the two indices. In other words, there's no ambiguity when I'm talking about lowering or raising this. If I am lowering alpha, this especially is not the same thing as A alpha comma beta. So I know just which side the index resides, and when I'm lowering it, I know just where it will reside even when it is covariant instead of contravariant. But now you see for the metric tensor, this is the same thing as G nu mu. And so if I were to lower this, this is the same thing as G nu mu or G mu nu. So you see, first of all, the two indices are actually on just one object, and secondly, it is symmetric between these two. So this method of trying to raise two indices and lower this, or when you have an index on an expression, you can just do this or that, doesn't apply especially here. It doesn't apply here. And this is one exception that I can think of to this rule, and I've just explained to you reasons why I believe this doesn't work here. Yeah, I'm sorry it doesn't always work, but I think I'd rather be honest with you than to mislead you into thinking that that method there always works. So it doesn't. And this is an example where it doesn't work. So I've stated again, it's because we have the two indices on one object, and secondly, this is symmetric. And so we can't hope to apply that method here. In a situation like this, you are just safer using the metric tensors in lowering or raising. Okay, so that's not about the remarks I wanted to make. Now, moving on, we have obtained the energy momentum tensor in our previous lectures. We have shown, especially using the Maxwell, well, what we call the Maxwell-Lagrangian for classical electrodynamics, and it was made of just this part. And it was with this Lagrangian, that alone, excluding this part, that we've calculated the stress energy tensor for classical electrodynamics. And then we showed that it was conserved. Now, but that's not the case if there are sources or external forces, in which case the Lagrangian will look more like this. And then finally, the Maxwell equation, this wouldn't be, of course, it wouldn't be zero in this case again because we have sources present. And also, because of that, if you remember also, we made an assumption in the term that we added to our energy momentum tensor to make it symmetric. Of course, it's still not unique even in the end. To make it symmetric, we made an assumption that F mu nu comma nu, for instance, is equal to 0. This was particularly useful in the term that we had to add, the additional term that we had to add to the energy momentum tensor we obtained using the expression that we had in that lecture. So in this case now we have sources or external forces, and so the Lagrangian looks different, and this is what we have, this is what is new. And the Maxwell equation looks like this being equal to that. Of course, that is simple. You can always use the Euler-Lagrange equation, like we have also used or derived by method of variation in our previous lectures. And also, either using this method that I've just explained very simply, we have illustrated that method in deriving our energy momentum tensor. That was done using this method quite easily, or whatever traditional method, but I think it's not too much of an exercise to be able to show using the Euler-Lagrange equation with this Lagrangian that this is equal to that. Of course, in our notation, we've tried to also make a distinction. You have to be careful which you are using. This originally will look, oh sorry, this should be alpha here, and this is A beta minus. Then this will be here beta A alpha. However, if you are using this notation of commas, you can see it's reversed. So it should be beta comma alpha. Of course, you know this means that actually, and this means that. So in the Lorentz gauge, again, so we're taking correction. In the Lorentz gauge, which means that, we can simply write out this equation. That is not too much of a big deal, but well, let's just go ahead and do it. So let me erase some of these things here that we've written out. In the Lorentz gauge, what we have over there is F mu nu, comma nu equal to 4 pi all over C J mu. And this, of course, what we've got here is the mu inside the bracket nu minus the nu A mu. And all this is comma nu equal to 4 pi all over C J mu. And I can take this in with this comma again. I think it's better for me to say this is the same thing as, again, the nu has to be down. The mu A nu minus the nu A mu. So if I were to evaluate that, I could write this as some d mu. The partials commute, so I bring this in, minus, I have here d nu, but a mu. That's what that is equal to. So in the Lorentz gauge, like we've said, this of course is the same thing as the a nu comma nu, and this is 0. And if that is 0, then that term is 0. And so with that, of course, we can see that what we are left with is this expression, which might as well be this. And this is the same thing as d-Alembert, not d-Alembert squared, just d-Alembert. So you might make the mistake, well, some use this notation, just the box. But either this or that is just the d-Alembert. I'm more conversant with this. In fact, I prefer this because it helps me understand that it's the analog for that. So just d-Alembert and not d-Alembert squared. So with that, again, we can see that, of course, this is the same thing as 4 pi all over c j mu. So what we are left with is some minus d-Alembert of a mu equal to 4 pi all over c j mu, which explains the minus that we have here. So one other way in this notation that we're using here is to have that equal to that. And what this means is just, so let me explain this notation a little bit. What I have here is mu comma alpha. What this just simply means is the alpha a mu. So that's what it means. Sometimes, especially I think this is peculiar to Weber, Joe Weber's book on gravitational waves, and maybe Picton too, their book Misner, Ton and Wheeler. Sometimes they add a comma here. I'm trying to be very careful because remember that when we talk about the definition of a covariant derivative, we have the definition for a covariant and the covariant derivative of a vector and that of, well, we can say a vector, a contravariant vector like this, or a covariant vector. And sometimes having to move these things either up or down could lead to that confusion. But well, whichever works for you. Personally, I prefer not to put the commas on top. So anytime when I have this, even if it's not the same like in this case, let's say for instance a mu comma alpha beta. What this simply means is the beta, the alpha, a mu. So if you see me write two sets of indices right after the lower comma here in this form, then we're just fine. Just take that to mean that these are just partial derivatives, and that's what it represents. Okay, that's that about that. So in the Lorentz gauge, we have that the Maxwell equations, which was that. This is actually the homogeneous part. This is just equal to that. Of course, in the homogeneous part, which we know, this might be the, I think, the most popular of all of them. In the homogeneous form, this is what we have. And quite remarkably, or in a very smart way, you could write that succinctly as this. Actually, where f alpha beta, the dual of f lambda nu, is defined as that. So it means when you differentiate, so we have shown this before, but just for the sake of completeness, let me just say that again. We've had a situation whereby if we were to write, of course, I might as well forget about, so I'll simply say alpha here, epsilon alpha, beta, lambda mu, where this is a totally antisymmetric tensor, being equal to 0. Or maybe I can say alpha, beta, lambda mu, the alpha, f, lambda mu. Oh, sorry, this is mu. This is summed over because these indices are contracted. I have this, so the only one that is not contracted here happens to be beta. And then in a way of performing a cyclic permutation, of course, this might as well be written as epsilon, beta, lambda, mu, alpha. And then I have here with me f. So well, let me put it in this way, comma alpha. This is the same thing as that. The alpha, f, lambda, mu. So let me just put it in this way, using this notation. I think that will make things easier for me. Now, if I have it in this notation, I can simply perform a cyclic permutation. It's summed over 3. But who is to say, for instance, that this is not the same as saying some alpha, beta, lambda, mu, okay, epsilon, beta, lambda, mu, alpha, f, lambda, mu, comma, alpha, plus epsilon again. I perform a cyclic permutation at this point in time, I am leaving beta alone, because what my business is with these three indices: lambda, mu, alpha, which is contracted. So beta remains where it is, and I have here mu, alpha, and lambda, and the same thing happens here: mu, alpha, comma, lambda, plus again I have beta, but then I have here with me alpha, lambda, mu, and then again here would become alpha, lambda, comma, mu. And then I said that this is these three things here are all cyclic permutations of these last three indices, which are all the same. So what you have in the end is some beta, lambda, mu, alpha in the end, with this all inside the bracket. F mu alpha comma lambda plus F here, alpha lambda comma mu. And of course, if this is equal to 0, that is definitely not equal to 0. And you're left with what is in the bracket to be equal to 0. So in every way, this expression here equal to 0 is equivalent to just all these three. One other way we can, of course, regardless of how we see it in this form, another way to see that this is 0 is to look at the fact that we can just consider evaluating this. In other words, when I have it written in this form, one thing we can do, for instance, is to say, given that these two are the same, we can perform some sort of symmetrization. Although we have a half there, but it's not that much necessary. But if this is all equal to 0, let me back up a bit. Let me just forget the fact that there is some equality here and go straight ahead in evaluating this expression, which is the alpha and that alpha beta, which in essence is 1/2 epsilon alpha, and here I'm guessing beta lambda mu, and this is so I'm going to have here with me some the alpha f, and this is here with me lambda mu. So one thing I can do here is simply to take note of the fact that when I have two expressions like this, well, let's just keep the two, I can try to symmetrize. In other words, I can try to look at two indices that, okay, first of all, let me just expand this. This f lambda mu is the same thing as me taking, what is it called? Writing this as the lambda a mu minus the mu a lambda. If I were to put this in, then the alpha f lambda, beta is equal to 1/2 epsilon of alpha beta lambda mu. Remembering that there's a d alpha here, so I have the alpha, the lambda for the first one, a mu, but minus, I have 1/2 epsilon alpha beta lambda mu. But then again, there's the alpha that is out here, but in here is the mu a lambda. I think that is quite straightforward. Yeah, so if you substitute this expression for that in this factor, remembering that the lambda is common to both of them, and all on the far left, this is what you get. Okay. Looking at these two expressions, we have dummy indices. And this dummy indices for this case, for instance, is lambda and mu. I can completely just interchange between one dummy index and another, and regardless of whether or not these indices are upon some totally antisymmetric tensor or not, I will be accruing no minus sign. In other words, this is just the same thing as 1/2 epsilon alpha beta mu lambda, the alpha, but then the mu, but then a lambda. This will be the mu a lambda. In other words, on this term, I have performed what we usually refer to as an interchange between lambda and mu. This is possible because both lambda and mu are dummy indices, and like I said, there is no minus sign or any kind of sign change associated with this kind of transformation. And this is what we get. And when you look at this, you can see, of course, that is, so I have the lambda, alpha, beta, lambda, mu, and then I have the, the alpha here, the mu, a lambda. Now with this expression, you can see that the two of them are the same. Of course, one thing you may want to consider is the fact that I can, by cyclic permutation, change this to that. That is one way to go about this. If I perform some sort of cyclic permutation, first of all, I can get this, well, if I decide to keep the alpha all alone where it is, this, like we've used up there, is the same thing as this lambda, beta, and this is the same thing as this again, lambda, beta, mu, and then again, this for me gives me back just where I started from here in this case. Well, there is no big deal with this, because what it simply just means is you have two things here that are exactly the same. I have here with me lambda, the alpha, the mu, and lambda here. These two are perfectly the same. This, like we've said, is totally antisymmetric. And so you have to be careful whenever interchanging any two of these indices, you are going to be getting a minus sign. And quite unfortunately for us here, of course, in this case, we already have a minus sign. But what I can do so far, for instance, is to pull this out. Okay, so as it is now, of course, everything is just okay. And looking at this one here, like we said, we make an interchange between lambda and mu because they're dummy indices. We obtain that. One thing we can decide to do is, of course, trying to make this the same as that. We have this already looking just like that. We have mu lambda here, but lambda mu. If I perform an odd permutation of just between lambda and mu, I'm going to get a minus sign, which changes that to plus. On adding these two quantities, I obtain that. This is what I have. Well, I can work with this, but then again, I can decide if I like to perform an interchange between, what is it called? Mu and lambda again, and I'll obtain this. But all that is not necessary. Well, with whichever one, for instance, if you observe this object, this is epsilon alpha beta lambda mu, I guess, yeah. And this is alpha here, and I've got here with me the lambda a mu. Well, one thing you have to note here is the fact that this object here will get a minus sign if I interchange alpha and lambda. And whatever interchange I perform between alpha and lambda here on this particular factor, it will always be symmetric. For instance, I can decide on this object to perform a total interchange, just the usual kind of interchange that we perform between dummy indices, alpha and lambda. We can't get any minus sign on this because this is just me changing one dummy index to another. And so this is the same thing as this, lambda, beta, alpha, mu. Then I have here with me the lambda, the alpha, a mu. However, this is the same thing as minus, but then epsilon, alpha, beta, lambda, mu. In other words, I just brought this alpha here and took lambda over here. That's what gave us the minus sign. The differentials, by the way, remain what they were, alpha, a, mu. But the differentials commute, so that in the end, I can write this as minus alpha, beta, lambda, mu, but then the alpha here, bringing this before the lambda, and I have this to be a mu. If you observe this, you can see that it's just the same with what we started here, what we started off with here. This is epsilon alpha beta lambda mu, epsilon alpha beta lambda mu, and then alpha lambda here, alpha lambda and a mu. And this is going to be equal to 0 because we just have something equal to minus itself. A equal to minus a implies a is equal to 0. So without us making any reference based on our knowledge of this homogeneous part of the Maxwell equation, we can just work in with this object here as it is defined for a dual tensor of this field strength tensor. All we can do by the property of symmetry and totally antisymmetric, the totally antisymmetric tensor, we have been able to show that the left-hand side on its own, working just with that alone, gives us 0. And this is a trick we are going to be using always. So when we have maybe let's say some f equal to one object multiplied by another one part of that factor is antisymmetric and the other one is symmetric. Anytime you have such an object, a combination of objects, it will always be 0. By symmetric and antisymmetric, I mean symmetric and antisymmetric with respect to both indices. Now, if you look at this, it's antisymmetric with respect to the interchange of alpha and lambda, right? And this is this antisymmetric with respect to alpha and lambda, and this is symmetric with respect to interchange of alpha and lambda. So it's antisymmetric with respect to the same, two indices, with respect to which this is symmetric to. So this can be antisymmetric in alpha and lambda, and then this is symmetric in some two other indices, say maybe beta and mu, and you expect to get 0. No, that wouldn't work. You can see just how that works here. So it's a general thing you find always, in QFT especially also, you find where you have two factors multiplying themselves, one antisymmetric, the other antisymmetric with respect to the same two indices. That object is always equal to 0. It's for the same reason, of course, like we've tried to explain here, it's for the same reason that we can find the conservation of this. Of course, there are other methods or ways by which you can do that. Yeah, so I think I can wipe this off very quickly and then we can talk about that. We have, of course, from our inhomogeneous Maxwell equation, that's just me trying to. This is what you have, of course. You can get this expression from this. I just wrote that some other ways here. So what we're saying is, if I were to differentiate the left-hand side of this expression with respect to x alpha, of course, raised in that form, we're trying to show that this should be 0. Of course, you know that this will be the same thing as some. So let me put the factors out. You have this to be some C over 4 pi. This is going to be the alpha acting on some the beta, F beta alpha. So take note again, this object, the field strength tensor, is antisymmetric with respect to the interchange of beta and alpha. But then again, these two factors or differentials are symmetric with respect to the interchange of alpha and beta. And this should be 0, and of course it is, like we have done before, and like we said, we are going to be using this often and on. And you have that, of course, by the usual method, interchange between two dummy indices. You don't get any minus sign for that, regardless of what the objects are that carry these indices. Interchanging between alpha and beta, these are just two indices. I have this to be the beta, the alpha, F, alpha, beta. No minus sign comes out of this interchange or transformation, because you just renamed one dummy index another, and you can name a dummy index anything on any one term, and there will be no consequence for that. Now here I can say, okay, well, I just look at these two indices, which is on the field tensor, and I put a minus sign, leaving these differentials the way they are, because I'm performing this interchange not between two indices, not between two dummy indices. It's just two indices on just the field tensor alone. When I perform that interchange, I get a minus sign because it's antisymmetric with that, with respect to that. Now, one other thing again, of course, like we've always said, is to once again try to perform the transformation that we started with over here between alpha and beta again. And this time we are going to get minus, but then again this will be alpha, and then this will be beta, this will be F again, but then alpha and beta. And you can see that when I perform that interchange, oh, by the way, no, sorry, that will be messing everything up. I don't need to perform this a second time. All I need to do, sorry, is simply to perform an interchange between this and that, which is allowed because the differentials commute, or it is symmetric. So this is what I get. So sorry for that, please. So this, just interchanging these two, you don't get any minus sign, and you can do that without necessarily have to say interchanging between two dummy indices. And when you do that, you can see, of course, that this again is the same thing as that. And again, which we have just shown that one thing is equal to minus itself, which in the end is equal to 0. And so this implies the conservation of the current density, this being equal to 0. So this is one way by which, again, you can show that current density is conserved. Okay, now these were some remarks we've made. Now very quickly into what, of course, we had already intended, we originally intended this lecture for, which is for the fact that we now have a symmetric tensor that, excuse me, we have here a symmetric tensor which we have derived or which we have this time around, but not for free space, but in the presence of external forces or sources. And so what we have here, by the way, is that alpha, beta, and 1 over 4 pi. And we have here G, alpha, mu, F, this lambda, beta, plus 1 over 4 F. Okay, sorry, I need to put the metric tensor over there. And this is F mu lambda. So we want to show that, we want to show or get the conservation law for this, and what we are going to see in the end is that this is really not conserved like we always know. In other words, that this alpha beta is not 7. What is it going to be then? Our method of working this time around will differ a little bit from what we usually do, but it's quite simple and easy. So I'll just go by that. Now I have this to be 1 over 4, and it will mean differentiating this G alpha mu, F mu alpha. Okay, no, that is not alpha, that should be lambda. F mu lambda, and this is F lambda beta. Now plus 1 all over 4, the alpha, G alpha beta, F mu lambda, F mu lambda. So usually I will say, well, since you have alpha and beta in the expression, write the stress energy tensor with indices already that are not already contained in this object. Well, by that method, of course, we are going to arrive at the solution, but then you will have to fuse with a lot of especially because of the metric tensors here, you may have to fuse with some Christoffel symbols. Well, that is just another method. Well, if it becomes necessary, we may do it by that, but in the light of what we're doing right now, we can just go with the very more elegant method now that we have. I can use this metric tensor to raise this alpha, and it becomes the mu, and still acting on the rest of the factors on that term, and then plus 1 all over 4, I do the same thing here, but then this will be the beta, F mu lambda, F mu lambda. Okay. One thing we can do, of course, is to simply just open up these brackets or whatever to see what these expressions will give us. Lambda, but then comma. In my notation, I'm going to put mu on top this way, keeping this constant, plus I keep this constant. I have here with me lambda, beta. I put the comma down, and then the mu top. And then next I have here plus 1 all over 4. This is F mu lambda, comma, with some beta on top, leaving this constant. So, okay, maybe I will have to do this. Well, plus 1 over 4 again. I'm going to keep the first factor constant, but differentiate this, comma, but then the beta is on top. And this is what I have. Okay, so looking at this expression, again, so maybe we are going to make use of one of the things here that we have. We have here with us some F mu nu, comma, nu to be equal to 4 pi all over C J mu. Okay, I can decide once again to do what I've said we can always do. Raise and lower, so whatever it is I used to lower this mu, I might as well use also, of course, if I'm lowering mu, I'll be lowering it on both sides. That wouldn't be a problem for me. So sorry, what I meant was whatever it is I use in lowering this mu, I might as well use in raising that mu. Yeah. So these two, of course, you can see are equivalent depending on how suitable we may find them. So I have an expression here that says, okay, well, in this case we have, we might have a situation because in terms of the order in which they occur, or they appear, I may have to be careful with this one. What I have here is some F, this is supposed to be mu, lambda, comma, mu on top. And you can see that in this case, I have mu nu, and the next thing is comma nu on top. Now it should have been lambda mu, comma mu, but now I have mu lambda, so this should give me a minus 4 pi all over c j subscript lambda. And that's what this object here should be. And now here also this comes along for the ride. So in other words, I have here with me 1 all over 4 pi, and then I have here with me minus 4 pi all over c j sub lambda f lambda beta. Now this is going to be plus. Then I have here a couple of objects. Well, let me just write it out first. And then this is going to be lambda beta. And remember the comma down, mu on top, plus. Looking at these two expressions, we can see something here that might work out in our favor, especially something that I've also fronted. First of all, again, like I said before, this is the field tensor. Totally covariant in this case. The mu and lambda here, like we have talked about initially when I was making a remark on this metric tensor. The field tensor in this case isn't just, in the way it's written down, of course, you know, if I were to expand this out, if I were to expand it, this f mu lambda, for instance, actually means the mu a lambda minus the lambda a mu. So these two indices are not actually on just one object. And secondly, the two indices are antisymmetric with respect to their interchange on this field tensor. So the trick that I talked about right from the beginning actually works here as opposed to this place. So now again, at this point in time, for the sake of convenience, I would like to do something like this, which will be the fact that on raising mu, whatever metric tensor I use to raise this mu, I can use to lower this one. And the same is applicable also for the lambda. So this object I can simply rewrite as 1 over 4, but f mu lambda on top with still the comma, beta following us, and then this time around these two come down. And then plus again 1 over 4 f mu lambda, comma, beta. Yeah. My reason for doing that, of course, you can see that these two are just the same. It doesn't matter the order in which they occur, but you can see that this object is exactly the same as that, and this is the same as. So adding the two, I have 1 over 2 instead of that. So I think at this point I will erase what I started with here. Moving on, we have that the alpha of this energy momentum tensor is some 1 over 4 pi minus some 4 pi all over c j here sub lambda f lambda beta. I have here also plus, this time here mu lambda f here lambda beta, but then comma mu. Then I'm going to have here plus 1 all over 2. I have here with me f. This is mu lambda comma beta, and then I have here with me f mu lambda. And this is what I have. So I simply have twice of that. So that's the reason for the 1 over 2 there. Okay, now let me just try to work on these last two terms. These last two terms I can write as 1 all over 2 of some f mu lambda down. Okay, yeah, exactly, because f mu lambda is common to the two of them. But then again, I'm going to have some 2 lambda beta comma mu here, and then I'm going to have plus. This is f mu lambda comma beta. So those two terms combined together in the form is given by that. And take note, of course, that if I were to evaluate this bracket, the half here will cancel these two, and I will be left with just this multiplied by that, which is this first term. And of course, this one here combining with this gives us that back. So one thing we can try to do is on this term we can write this as f mu lambda, f here lambda beta comma mu, plus f again lambda beta comma mu, yeah, plus f mu lambda comma beta. So what I want to do right now is simply to find a way. Of course, you probably could guess already where I'm going with this. I'm trying to write the contravariant analog of this expression. So everything I'm going to be doing right now is to perform a manipulation that will lead me to be able to rewrite this. So on this object, for instance, I can just take these two factors together. Let me just look at these two factors. These two factors combine. This is the same thing as, okay, I think I don't need this below anymore. Factors combine is the same thing as F mu lambda, F lambda beta comma mu. Now, if I perform the kind of interchange we used to between lambda and mu, remember, this is an interchange between one dummy index and another. And not just an interchange on this field tensor. If it were just an interchange on this field tensor without affecting anything here, then I'll get a minus sign. But this is just me changing one dummy